my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
For the past 40 years, astronomers have known that something about the cosmos doesn't add up. First in galaxy clusters, and then within individual galaxies, they found that visible matter, stars, gas, and dust, cannot account for the motions they observe. No one knows what this missing mass, now called dark matter, actually is. But studies by NASA's WMAP spacecraft of the cosmic microwave background, the oldest light in the universe, show how much is out there. Dark matter outnumbers ordinary matter by 4 to 1. The WMAP results also hint that dark matter likely takes the form of an as-yet undiscovered subatomic particle. WIMPs represent one hypothesized class of these particles. They neither absorb nor emit light and don't interact strongly with other particles. But when they encounter each other, they annihilate and make gamma rays. That's where NASA's Fermi Gamma Ray Space Telescope comes in. 2 years of scanning the sky with Fermi's Large Area Telescope have set the strongest limits yet for WIMP dark matter. The best place to look for gamma rays from dark matter annihilation? The most boring galaxies around, called dwarf spheroidals. These faint, tiny galaxies possess impressive amounts of dark matter, but they contain no gamma ray emitting objects and little gas or star formation. In the currently accepted cosmology, the first structures formed as the gravitation of dark matter corralled normal matter. Simulations show that the largest structures formed in this way were comparable to the dwarf spheroidal galaxies we see today. It's thought that large galaxies, like our own, were built up from collisions among these dwarfs. Using 2 years of data, Fermi scientists explored 10 dwarf galaxies for any sign of gamma rays from WIMP annihilation. In this graph, the dashed line marks the sweet spot where conventional expectations for WIMP dark matter align with what we know about our universe. Even when scientists combine all of the Fermi data from all 10 of the dwarfs, they see no sign of gamma rays. This limit shrinks the box where WIMP-based dark matter may be found, and, for the first time, shows that the cosmology we know essentially eliminates some WIMP types. The longer Fermi operates, the better its ability either to box in the nature of dark matter or to find actual evidence of what it is, and the discovery of new dwarf galaxies will make this search even more sensitive. Although nondescript, dwarf spheroidal galaxies may have been the first large structures to form in the universe. Now, they've taken center stage in the drama to solve one of astronomy's greatest mysteries. Dark matter makes up about 27% of the cosmos, but so far no one knows what it is. Dark matter neither emits nor absorbs light, and it interacts with the rest of the universe primarily through gravity. In fact, it's thought dark matter traced the initial framework of the cosmos, attracting normal matter that formed stars and galaxies. Black holes are astronomical objects famed for their extreme gravity. Jeremy Schnittman, an astrophysicist at NASA's Goddard Space Flight Center, wondered if they could serve as a kind of laboratory for exploring different dark matter models.
The leading particle physics model for dark matter is called weakly interacting massive particles, or also known as WIMPs. These guys just fly through the universe without even bumping into anything or each other. The idea of two WIMPs coming together, annihilating and forming gamma rays is kind of like two bullets hitting head-on in a crossfire. It's very rare. But when you go to the area around a supermassive black hole, we expect the density to be much higher, so the probability of annihilation is much higher in this detection with a gamma ray telescope.
In Schnittman's computer simulation, a population of dark matter particles orbits a rapidly spinning black hole. Close in, at the brink of the black hole's event horizon, the particles are orbiting at nearly the speed of light. The lightly shaded region farther out is the ergosphere, a zone where all particles are forced to move in the same direction as the black hole's spin. The concentrated dark matter collides and makes gamma rays, but not all of this light can escape the ergosphere. The gamma rays most likely to make it out come from the left side, where the black hole spins toward us. The result is an asymmetric glow. The highest energy gamma rays come from the center of this region, corresponding to the black hole's equator. Schnittman's work has uncovered previously overlooked orbits that can produce extremely energetic gamma rays, and has shown that the peak energy attainable for this escaping light is a strong function of the black hole's rotation. So far, the initial work is focusing on setting upper limits on dark matter annihilation rates by looking at otherwise quiescent galaxies, but Schnittman's ultimate ambition is nothing short of an unambiguous detection of dark matter annihilation around supermassive black holes.
To me, dark matter, black holes, two of the most elusive things in the universe coming together to help explain each other is quite poetic.